right, Scientist Roger's back to continue this experiment. So where we left off, we had the standard clear glass globe, and the glass globe did not have anything different than a standard at-home bulb. But I have this bulb here. I grabbed it earlier in our video by accident. The only difference between these two light bulbs is, well, one has clear glass and the other has a tinted glass. This is called a frosted bulb. So the insides are completely identical. But what's nice about this is sometimes light's bright. Has anyone ever walked in and flicked on the lights when you were sleeping and it almost stings your eyes? Well, one of the things about these frosted bulbs is it makes it a little less harsh on your eyes when you first see it. It kind of dampens a little bit. So what I found interesting is I wanted to see if you could recognize when we connect our little experiment and see if we can acknowledge the filament glowing. So, Miss Frank, can you zoom on in? We're going to do the same thing. We're taking the wire, we're placing it on the thread. We're taking the other wire, placing it at the end of our train of batteries over here. And we're going to place it on and see if we can also have it light. Ready? 3, 2, just kidding. One thing I want to point out, again, it has to be matched up positive to negative. And one of the things, the reason why I want to point that out is, imagine if it was negative to negative meeting. That means both of these are kind of like having a tug of war. Realistically, they're pushing against each other like a sumo wrestler because both of the energies are trying to come out this way towards each other. In this case, this probably would be more of the tug of war. These sides are trying to absorb or take the energy from either side. So, in order for this to flow properly, the energy goes in through the positive, out through the negative, in through the positive, out through the negative, and around our circuit. So, let's see. We've got our negative to positive collection of cells. We're going to place one wire on this thread, this wire on the end, and technically I could turn this bulb if I wanted to and put on the tip, but I feel like it's easier for me to hold it this way. And Miss Frank, on the count of 3, we're going to see if we can see it on a frosted bulb. Ready? Count us down.
3, 2, 1.
Do you see anything?
Very faintly.
It's very, very faint. And you'll notice that we could see it in the clear bulb, but it's really hard to see with this frosted. That kind of goes to show the fact that the frosted globe makes it a little bit softer light. Now we have the main event, Miss Frank.
Woohoo.
We've got all these cells, all this energy, all in a row. What happens if we connect it with this bulb? An explosion! All right, well, when I think of explosion, I think of things exploding all over the place. Not quite. We wouldn't be doing that in school, of course. Instead, we know that in our bulb, we have a filament. And what I'll tell you is, this has a much more expensive filament than this. A little tiny test classroom bulb. This is a real actual light bulb that lasts for about a year in our house. This one, maybe an hour or 2. It's not a high quality filament. So what happens is when all the energy passes through it, it is going to disintegrate this filament. Now you're gonna have to look closely as we connect it because it's not gonna last long. Are you ready? Are you steady? 3, 2, wait, are you zoomed in enough?
I'm working on it.
All right, 3.
Wait.
Okay.
All right, we're
2. You sure you're ready?
We're ready.
1. Nothing happened.
That was disappointing.
That was just, let's try a different bulb. Alrighty. Hopefully this works. Ready? 3, 2, 1. There we go.
Whoa.
Now what we noticed is we had a bright flash light, almost like a camera taking a picture. And now, if I were to just take the single cell, single bulb, it normally should light, and this wire is hard to manage. Now it will not light, and the reason why, I wish you could see it, is there is nothing in between the two support wires. That flash, that amount of energy passing through, caused so much energy to go across it that it actually burnt up the filament. If you turn it over, you can kind of see some of the ash and debris of the filament. It is no longer in place, and if there's no filament, there's no way for the light to light up, okay? So let's try this one more time. I want to just test this bulb because we like fireworks, as long as they are professionally maintained. All right, let's make sure. Oh, looks like we have a dead bulb. Miss Frank, can you run and grab me a real quick bulb? I'm not satisfied with that being the last. As Miss Frank is doing that. Again, in our light bulb, we have this filament that travels across, and part of the neat attribute of the filament is it purposely glows. The more energy you have passing through the light bulb, the less time that filament's gonna last, and your bulb's gonna die quicker, okay? So if you have a little bit of energy, then that filament's gonna last a long time. If you have a lot of energy, then that filament's not gonna last nearly as long. I'll give you an example. This is a little bit of preview. If your energy is 2 times as strong as our standard circuit, our filament will last. Now, if you said 2 times longer, we said the energy is 2 times more, it would actually be half as long. We'll come back to that a little bit later, but let's singe some filament. Hopefully this one's not a dud. Are we ready? Are we steady? 3, 2, 1. And there you go. So much energy passing through this circuit, causing this filament to disintegrate because too much energy is passing through. Hopefully you like our lights display. I know it's not quite the same thing as 4th of July, but not bad for a day at school. See you next time.